All right, let's dive into a problem that sounds almost ridiculously simple, but is actually a huge deal for our food supply. How do you measure a field of grass? I know, it sounds easy, but for farmers, it's a massive challenge. And today, we're going to look at how a totally new AI approach is completely changing the game. No, really, think about it for a second. To manage a farm properly, you need to know exactly how much food, how much biomass is out there in your pastures. If you have too many animals, you end up ruining the land. Too few, and you're just not being efficient. So how in the world do you get that perfect number, right now, across hundreds of acres? Well, for the longest time, the best method was literally called clip and weigh. I mean, the name says it all. You'd have to go out into the field, physically cut a small square of grass, dry it out, and then weigh it. As you can guess, it's incredibly slow, it's destructive, and there's just no way to do that at a large scale. So the goal here was to create something way better, an automated system that could just look at a picture of the field and instantly tell you the answer. Okay, so the goal is to use images. But how do you teach a computer to see grass and actually understand how dense it is? Well, the first step the researchers took was to build a specialized AI right from scratch. They started with a tool called a convolutional neural network, or a CNN. The best way to think about a CNN is like a brand new apprentice that you're training for one and only one very specific job. You give it thousands of pictures of pasture, and you tell it, okay, this is what a lot of grass looks like, and this is what a little bit of grass looks like. You're training it from a blank slate to do just that one. And you know what? It worked. Sort of. It gave them a decent baseline to work from. But the problem is a real pasture isn't like a perfectly manicured lawn. It's a messy, complex mix of green grass, dead matter, clover, weeds, all sorts of stuff. And that custom-built CNN, it just really struggled to make sense of all those fine details and variations. It was a good start, but it wasn't the breakthrough they needed. And this is where the story takes a really fascinating turn. Instead of trying to teach a brand new AI from scratch, what if you could use an AI that already has a deep, general understanding of what the world looks like? This is where something called a foundation model comes in this case one called DINOv2. This is a total game changer. So forget this specialist apprentice we talked about. This is like hiring a master artisan who's seen millions of different images of, well, everything. Cats, cars, mountains, you name it. It hasn't been trained specifically on grass, but it has already learned the fundamental rules of texture, shape, and depth that make up our visual world. And as the researchers themselves put it, a model like DINOv2 is a superior feature extractor. It's just incredibly good at looking at an image, any image, and pulling out the rich, meaningful data. And the real key here is that it works really well even with a smaller set of pasture photos, because its existing knowledge is already so vast. You don't have to teach it what texture is, it already knows. So the new process became this really clever two-step pipeline. First, you show the pasture image to DINOv2. It doesn't give you the final answer, but what it does is extract all these sophisticated visual features. It turns the image into a rich set of data. Then you feed that data into a second model, in this case, one called CatBoost, which is brilliant at taking structured data like that and making a really precise final calculation. So the big question, right? Did this more complex two-step process actually work any better? Well, the answer is a huge, resounding yes. Let's look at the data. Okay, check this out. This chart shows the performance improvement over that original basic CNN model. The first attempt, that optimized CNN, gave them a respectable 27% boost. Not bad. But look at the massive jump when they switched to the DINOv2 pipeline. The first version got a 120% improvement, and the final refined model using both DINOv2 and CatBoost, an incredible 150% leap in performance. It's not even in the same league. Now, for the raw numbers, the key metric here is something called weighted R2. You can just think of it as an accuracy score. Higher is better. The baseline CNN scored about 0.25. The final DINOv2 model hit 0.6289. That's more than double the accuracy, a massive jump. That means far more reliable, trustworthy data for farmers. Let's just isolate that final number for a moment, because it's pretty wild. A 150% improvement. This isn't just a small, incremental step forward. This is a fundamental change in how well we can measure and understand these natural environments just by using a camera.
So, why does getting a better grass measurement matter so much to the rest of us? Well, this technology connects directly to some of the biggest challenges we're facing on a global scale.
Believe it or not, this project directly supports several of the UN Sustainable Development Goals. By enabling much better feed management, it contributes to zero hunger. By preventing overgrazing and waste, it supports responsible production. And by helping to keep the land healthy and preventing soil degradation, it has a direct impact on life on land.
And really, that's the whole point. This isn't just a cool AI experiment, it's a tool that provides better data. And better data allows farmers to make much smarter decisions, which leads to healthier ecosystems and, at the end of the day, a more sustainable and secure food supply for all of us.
And that kind of leaves us with this final mind-bending thought. We started with the simple challenge of counting blades of grass, and we ended with an AI that has a fundamental visual understanding of the world. So, if it can learn to see and quantify something as complex and chaotic as a pasture, what's next? What complex system can't it learn to see? From monitoring coral reefs to analyzing medical scans, the potential for these foundation models to help us understand our world is just beginning to unfold.